So the first speaker of this session is Marcin SROKA, who received the International Stefan Banach Prize for the thesis defended at Jagiellonian University. Now he is a postdoc at Centre de Recherche Mathématique in Montreal. The topic of the thesis was Monge-Ampère equation in quaternionic spaces. This line of research was initiated by Alescher, Harvey-Lawson, then Verbitsky. The solution of the equation corresponds to possibility of trivialization of canonical bundle on so-called hypercolor spaces with torsion, HKT for short. Marcin SROKA, so his thesis contains results of 3 papers. 2 of them deal with the Dirichlet problem in domains of quaternionic space. So the results he obtained were existence and regularity results, existence for the right-hand side in LP, P bigger than 2, and this number 2 is sharp, existence of bounded solutions, and then in the second paper he obtained Helder continuity of those solutions. And the last paper concerns a conjecture of Alescher and Verbitsky, which is an analog of Calabi conjecture in Keller geometry. But this conjecture deals again with HKT spaces, manifolds. It can be phrased like this, that given a volume form on HKT manifold, you can find a metric, Riemannian metric, for which which realizes this volume form. So the volume coming from the metric is the given one. The typical way of attacking such problems is the method of continuity, which means that you solve the family of equations parameterized by, say, interval 0, 1, and you want to prove that the parameters for which you have solutions, this set of parameters is open and closed. To get it closed, you need to prove a priori estimates, C1, C0, C1, and C2, and C2 plus some epsilon. Because in such spaces, you work in some Helder spaces. So Marcin SROKA obtained a new proof of C0 estimate, which was given before by Alescher and Shelyukhin. His proof was much simpler and shorter. So that was the last result of the thesis, and the follow-up is that after his PhD, together with Sławomir Dinew, who is here, they were able to prove the conjecture, but in the special case of HK manifolds, which means hypercolor manifolds. Thank you.
Thank you very much. So firstly, thanks a lot for being here and for giving me the opportunity to speak here. And of course, I would like to thank the committee, because I think I realized some faces which actually granted me the prize. So I thank you. Okay, so the plan is I would like to so Professor Kłodziej actually summarized everything, so we could have went home already. But let me speak a little more about the details, but I will speak only about the details of this part of analysis which corresponds to this original geometric problem. So in my thesis, I also had these rather technical results about the Dirichlet problem. I will forget about that completely and focus on the original conjecture, which actually stimulated the research on certain PDEs, on certain equation. Okay, so in order to do that, I will spend a couple of minutes to recall some ancient history. So let me recall you, or let you know, that a complex manifold is, and all the manifolds are compact in this talk, is a compact manifold endowed with a field of endomorphism, so some transformation of the tangent bundle, which satisfy the property that when you square this endomorphism, you obtain minus identity. So this acts as an imaginary unit and allows you to treat at each point of the manifold the tangent space as a complex vector space. Okay. So this requirement is only being an almost complex manifold. Now, being a complex manifold actually means that this structure has to be integrable in a certain sense, which means that you can find a local coordinates in which the coefficients of this tensor are constant. This is written precisely in here. So now those x's and y's, when you patch them together, so you write the letters z equal to x plus iy, they will be an honest complex coordinates for your space. Okay, so this is a complex manifold, and now on a complex manifold, it's reasonable to consider only certain Riemannian metrics, namely those which are compatible with a complex structure, because otherwise you have actually forgotten that you have a complex manifold. You would only deal with the smooth structure. So those special Riemannian metrics are called Hermitian, and those are precisely these which satisfy the fact that the Riemann tensor is invariant with respect to I. So in terms of local coordinates, it means that in these holomorphic coordinates, which has to exist, this Riemannian tensor has to be presentable in that way that it's given by some Hermitian matrix G alpha beta bar, and this fancy letter here means a symmetric product. So this is the letter for this tensor that plus that tensor this. Okay, great. So now, those kind of metrics appear in many places. So they naturally appear in the mathematical physics, in string theory, for example, but they also naturally appear in Riemann geometry already. For example, in the classical theorem of Berger, the classical theorem of Berger tells you that the building blocks for the Riemannian manifolds have some background geometry additional to the metric one, and those additional structures are either real, complex, or quaternionic, depending on what is the holonomy of the Levi-Civita connection. And today we will be focused on those two cases when we have an additional structure, complex or quaternionic. So once you have a complex manifold with a Hermitian metric, it's pretty customary to switch a language. So now, instead of dealing with a real object, since your manifold is complex, you would like to still consider the same objects, but just in complex language. And this complex language is obtained by taking, for our use, only the original metric and the Ricci tensor of the original metric, and just plugging I to the first coordinate of those two tensors. So this operation will actually create for you out of those not symmetric tensors, but exterior differential forms. And exterior differential forms are more flexible. It's better to deal with them than with the symmetric tensors. So that's one of the reasons why we are doing that. I have written even precisely for you that the resulting differential forms will be of type 1, which just means that you can write them down locally in terms of one unbarred differential and one barred differential, and the matrix of coefficients has to be a Hermitian again in order for those forms to be real, and they were real. So now, a very special type of Hermitian matrix are the Kähler ones, and the Kähler metrics are precisely the one which we saw in the previous slide, namely there are many equivalent conditions of being a Kähler metric, but one definition is that a Riemannian metric is Kähler if its holonomy is contained in the group UN. Okay, this is one of the definitions of being a Kähler metric. And you can show, it's not very hard, that this condition under the Riemann assumption is actually equivalent to this form which we just obtained in here, being declosed. Okay, so this is certain additional integrability condition for your metric. This is a differential equation, if you like. And such a metrics have very, very nice properties. Many theorems hold for those metrics, but not for general Hermitian metrics. This is not this sort of or not this level of abstraction, but a nice property or which follows from my Kähler condition is that this Ricci form, but remember now we made a differential form out of that. First of all, it's closed, but moreover, it represents a canonical cohomology class, which you can define on every complex manifold. So having a complex manifold, there is a way in which you can define a very special cohomology class, which is called the characteristic class, even the first Chern class. And it turns out that for the Kähler metric, it will always be the case that this guy will land out in this cohomology class. Okay. And now we are coming to the sort of root of all the problems I was dealing in my thesis. So there is a very old conjecture, actually now a theorem of Calabi, which was posed in 1954 in the proceedings of ICM. So I've just told you that when you have a Kähler metric, Ricci of this metric is always in C1. The question of Calabi is the reverse true? Is every guy there actually obtained by this process? Is every guy there Ricci of some Kähler metric? Of course, I'm cheating a little bit in here. Not every guy in here is eligible to be Ricci of something. You have to restrict. So some necessary conditions have to be satisfied. This guy has to be a real form because we are obtaining only those guys in here and of type 1,1. But if you have those assumptions, then you are truly asking, is every guy having these necessary assumptions of the form Ricci of some Kähler metric? So this was the Calabi conjecture. Actually, in the beginning, it was a theorem, but there was a gap in the proof. So, and it took a nice amount of time to repair that. Okay, so let's now discuss very briefly how to try to solve this issue. Okay, so how do we attack this problem? How to find omega prime having rho given? Okay, so it turns out that on a Kähler manifold there is a very nice property which is called DD bar lemma, which tells you that if you have another Kähler metric, and by some chance it belongs to the cohomology class of the original one. And you can always assume that, because if omega prime is going to exist, it will belong, for example, to the class given by omega prime. So you can assume that you are looking for some omega prime, which is in the cohomology class of the original metric. But having this assumption, it turns out that omega prime is this class, then it has to differ from the original one by IDD bar of some function phi. Now, what are DD bar? Those are first order differential operators which are naturally defined on every complex manifold. It's not important what they do precisely, but complex structure tells you canonically how to define those two operators, D and D bar. Okay, and then this guy is just an external differential form which somehow depends on the second derivative, certain second derivatives of phi. Okay. So that you know on every Kähler manifold. And now it also happened, well, you can also apply this knowledge to rho. Well, I told you in the previous slide that Ricci of omega belonged to the first Chern class, and we took another rho which is in the first Chern class. So again, the same argument tells you that those two have to differ by IDD bar of something yet another. Okay, and now those two information tell you that in order to have this satisfied, it has to be the case that the volume form of this new metric is equal to that one. This is still, there is one step hidden, but I don't want to go to any calculations in those slides. So this problem is precisely equivalent to solving this problem, and this problem is a PDE. It's a PDE because this tensor depends on the second derivatives of phi, and now this power means an exterior power. So you have this differential form and you take the wedge power of n copies. So we will be somehow multiplying the second derivatives of phi in the process of computing this form, right? And I'm asking, will the expression which I am obtaining here, will this expression be given to the right-hand side, which is fixed? Okay, so this is a PDE, and this PDE is called the complex Monge-Ampère equation. We will see in the next slide why. And so we have reformulated the original problem in terms of PDE. So the Calabi conjecture asks if you can solve this for every f, because every f corresponds to every rho. And this question was solved by Yao in 1976. One of the reasons which was given in the citation as the reason for the Fields Medal, because solving a PDE, nonlinear PDE in particular, on a manifold is not an easy task. So, but this is an ancient history. I will tell about some more recent results in a second. And you just justify very quickly why this is called the complex Monge-Ampère equation. So this was the equation. So now, how to compute this volume form? Well, you have to look what is the local expression for this guy, and the local expression for this guy is something like this, but plus ID bar of phi. So here you have plus phi dz alpha dz beta bar. Oh, I have it in here. So this equation here is nothing but the determinant of this, because this is a trivial linear algebra. If the coefficient of this form are given by the g plus phi, then this guy is exactly the determinant. So this equation is the determinant of that equal to e to the power f times the determinant of that. This is given because g is some initial data, and those are the second order derivatives. And the equations of the form determinant of the real Hessian are called Monge-Ampère equation. So this is the determinant of the complex Hessian, because here you have the complex derivatives. So this is called the complex Monge-Ampère equation. Okay. So now, if you choose the coordinates in such a way that this matrix is diagonal, which you can always do, then what is the determinant of the matrix? It's just the product of the guys on the diagonal, right? And moreover, this is an invariant quantity. So whenever I denote by lambda 1 to lambda n the eigenvalues of this matrix, then this guy is precisely the product of all of them, right? So this equation is precisely given by the product of the eigenvalues of G plus complex Hessian equal to e to the power f. Okay? Great. So after this problem was solved, a lot of research was dedicated to some other equations of the eigenvalues of the complex Hessian on complex manifolds, some of them having some of them being geometrically meaningful, some of them being analytically meaningful. But in general, the equations which were treated were of the form, you take some small f, which is just any function which does something symmetric to n variables, and then you feed this function with the eigenvalues of the complex Hessian. So in particular, if you take f to be just the product of all of them, you will recover the complex Monge-Ampère equation, and you will be solving the original Calabi conjecture. Okay. It's not mandatory that you have to start with the tensor, which is of the form omega from the beginning plus the complex Hessian. You can do something more wide. For example, you can add some factor which depends on the gradient as well, or on the function as well. And in that cases, you, in general, write that you are taking omega plus some chi, which depends on all those quantities. And in general, the equations are a mess, and it's hard to have some satisfactory existence theorems. Nevertheless, you can deal with that, with those equations, and in some cases you can still say something meaningful. So just two results which I would like to underline are a good representatives of those equations are these which are called the K-Hessian equations. So they are obtained by taking not only the product of all those guys, but the sum of all, let's say, K products. Okay, and those are called the K-Hessian equations. And they were solved on Kähler manifolds not that long ago, actually, because the final touch was done by Dinev and Kłodzie in 2012. Their method was dependent of the second order estimate, which was obtained by Hu-Ma-Wu. So Hu-Ma-Wu obtained an estimate on the second order derivatives. in terms of the first order derivatives, but the first order derivatives are not known to be bounded. So Dinev and Kłodzi found a clever way how from this partial result you have second order derivatives bounded by the first order derivatives, how to squeeze from that first and second order derivatives have to be bounded. Okay, so of course somehow equation has to come into play as well in order to derive that. And this method became to be crucial for all the complex PDEs which are now treated, meaningful geometrically or not. And it's pretty powerful. Not powerful enough to deal with the problem which I will discuss in the second part. So some more general than Hessian equations were solved formally by Szekli-Hidi, but as I told you, his method actually depends on this method of Dinev and Kłodzi for obtaining the second and first order estimates. Okay, so just a final touch on the Calabi conjecture. So you can imagine a generalization of this problem. The original Calabi conjecture was you were given a Kähler manifold. Is every volume form obtained by omega plus IDD bar phi when the starting omega was Kähler? Now the question is, what if you drop the Kähler assumption? What if you have some starting metric, but of worse properties? Okay. So the general problem you can treat is as follows. You distinguish some class of Hermitian metrics. You distinguish a representative of this class. And now we are asking, is every volume form obtainable as a volume form for some guy from this class? Of course, it should be the case that the class is not conformally invariant. So it shouldn't be the case that if you have omega inside, then e to the power f omega is there as well for every function, because then you can solve this problem trivially, right? You can just divide by e to the power f, plug it in, and you have found the solution. But usually those classes, this class C is usually given by some differential condition, as in the Kähler case, d of omega equals 0. And this condition forces you that if you have a conformal transformation which is of the same class, it has to be a constant conformal transformation. So no trivial solutions in general, and the problem is well posted. So the problems of that sort are when you start with C, the collection of Kähler matrix Calabi conjecture, when you start with the set of the so-called Gaudichon metrics, and those are the ones for which IDD bar, not of omega, but omega to the power n minus 1 is equal to 0. Then you obtain the Gaudichon conjecture. So it was posted originally after the solution of the Calabi conjecture in, I think, 1984, if I'm not mistaken, but solved only 2015. And the PDE, which you have to write there, because there you have to change the perturbation. You are considering the metrics of that form is no longer enough. You have to put something more complicated in here. In other words, saying in this language which we have in here, you have to consider some raw chi. And then the analysis of the equation becomes pretty hard. Okay, but all of this motivated Alesker and Verbitsky to pose the conjecture, which is the main topic of this talk. So now the game takes place on yet one level higher analog of complex manifolds, which are called hypercomplex manifolds. So hypercomplex manifolds, well, the definition is in here. You just have to be endowed with 3 complex structure such that they satisfy the quaternionic relation. Because remember, they are already complex structures, so square of each of them is minus identity. So this is the one lacking one for the quaternionic relations. So likewise, you can treat each tangent space as a quaternionic vector space or module over an algebra if you want to be formal. But now you put less integrability on these kind of structures because you cannot put too much in order not to be trivial. So while complex manifold always locally look like Cn, like a piece of Cn, hypercomplex manifold almost never looks like a piece of Hn of the flat quaternionic space. And this integrability which we put, so just requiring that each of the complex structures separately is integrable, turns out to mean that there has to be a special connection which preserves the tree. And this condition in differential geometry is usually referred to as a weak integrability. When you have torsion-free connection in your reduction of the structure group, then it means you are weakly integrated. Okay, so yeah, this we already know. Now, on such a spaces, it's only reasonable from a similar reasons to consider hyper-Hermitian metrics. So those which preserve all the three complex structures. And like we did in the complex case, instead of playing with G and Ricci of G, we played with this omega and Ricci of omega, which were just twisted by I. Now you can assign to this guy another object, which still, and this is some differential form, again, second degree differential form, which encodes this metric completely. So just to say it quickly, instead of playing G, you can always play with omega and it does not forget the generality, okay? Now, a trivial observation is that these, well, you have to do the calculation, but the observation is the capital omega is of type 2,0. So locally, it's always readable in terms of DZs only, without DZ bars, okay? And this in turn tells you also, because this is defined by G, so it's non-degenerate, that if you take the top possible power of capital omega, it will give you the complex volume form on your manifold. Or if you know what it means, it will give you the section of the canonical bundle. Okay, so it means that the hypercomplex manifold always have a trivial canonical bundle topologically. And this will be important in a second. But before posing the conjecture, let me give you two possible examples of classes of hyper-Hermitian metrics now. So the classical one, again from the Berger list point of view, are the hyperkähler metrics. So the hyperkähler metrics are either, as here defined, those for which the Hermitian forms with respect to ij and k are 0, or, if you recall this Berger classification, those are that Riemannian metrics which have holonomy contained in SPK. Okay, so those are hyperkähler, and a slight generalization of a hyperkähler metric is a hyperkähler with torsion metric, as the name can suggest to you. So analytically, it's very easy to spell out what it means that you are hyperkähler with torsion. It just means that the capital omega is slightly less closed than in hyperkähler case. In hyperkähler case, it was supposed to be declosed, and now the exterior derivative is nothing but d plus the bar. So if you are d closed, then you are d and the bar closed. So this surely forces that, but this condition alone does not give that one because you are lacking the bar of omega equal to 0. So this is a weaker condition, and there are better reasons to consider such a metrics, but we don't have time to talk about them. So we are just taking this analytic definition of being hyperkähler with torsion as granted. Okay, and now
this operator is respect to which complex structure?
With I, yeah, that's a very wise question. Yeah, if I'm not putting any subscripts, then it means with respect to I. But I will comment then. Actually, having a hypercomplex structure is not choosing ij and k; it's choosing the whole twistor sphere. So I'm dealing with the chosen three. You can repeat all my presentation with other three you like, which you obtain by doing a rotation on a sphere. And formally, the equation, which I will write in the next slide, will be different in sense that the differential forms will even live in different bundles. But if you write the resulting equation by dividing sides, the equation will be the same. So we are only making a choice for writing an equation. Okay, and now having this, so Alesker and Verbitsky in 2008, having this setting, posed the following conjecture. So they noticed that, well, there are good reasons to believe that HKT metrics are analog of Kähler metrics, and you can argue that the complex volume form is an analog of a volume form. So why not consider the following question? Given any section of the canonical bundle, which is nothing but given any complex volume form, is there an HKT metric? Suppose even we require in the same cohomology class, certain cohomology of the starting HKT metric, such that the complex volume form associated to this metric we are looking for is the section of the canonical bundle we started with. Okay, so this is precisely the Calabi conjecture in quaternionic language. In the Calabi conjecture, we had volume form. Now we have complex volume form, and we are asking, is there a metric which has this prescribed? Okay. So now how to tackle that? Well, again, we would like to have some nice expression for omega hat, right? Ideally, in terms of some second order derivatives, then it would give you a second order PDE to solve. So it turns out that there are very natural differential operators on hypercomplex manifolds as well. Actually, there are even natural operators on the quaternionic manifolds, which I'm not talking about today. But in a hypercomplex setting, they have a very nice explicit formulas found by Verbitsky. So it's not important that we go into the definition of DJ and DJ bar. Those are, again, some first-order differential operators. And now Aleska and Verbitsky suggested that in this problem, you are looking for omega hat, which is the perturbation of the original by ddj phi. So those are first-order differential operators, some strange one. Then this is the second-order quantity. And if you, again, feed this relation with that omega hat, you will get such an equation, because you can always assume that this theta is of the form some conformal factor times any section of the canonical bundle you like. So why not the one given by the starting metric? And now if you write in the coordinates, you will obtain some PDE. And this PDE, in the analogy with the complex setting, is called the quaternionic Monge-Ampère equation. And this is just some elliptic second order PDE, which you try to solve. So, yeah, I think I have like 5 minutes or less. Okay, great. I will not argue with that. Then we can contemplate a little more. So now if you do some calculations, then you will obtain that the Riemannian metric on your hypercomplex manifold, which will be assigned to this perturbation of the original omega, is actually given by the original Riemannian metric plus what we would like to say averaged over quaternion's second covariant derivative with respect to the Obata connection. And you can argue that this guy should be called the quaternionic Hessian. Okay? So that also justifies the name, if you like. But now let us focus also what actually the equation asks you to do, like what it does. So what it does is, well, you can ask what are the eigenvalues of G phi, right? This is again some tensor. Well, the matrix of that will be a symmetric matrix. And because everything is invariant with respect to the quaternionic structure, the multiplicities of the eigenvalues will be divisible by 4. Because if you have some eigenvalue, this is a symmetric matrix, so it only has a real eigenvalue. So you have an eigenvalue, you have an eigenvector, then I of this vector will also be an eigenvector, and because this was a complex structure, it will be linearly independent with the first one. J of this resulting guy, also of this starting guy, also will be an eigenvector. So this discussion tells you that I haven't lied here. Truly, the eigenvalues have multiplicity 4. And now it turns out that this equation precisely asks you, take the multiplicities divided by 4 and they'll multiply all the eigenvalues. This is your equation. So this is your equation locally. Yeah, it's written here. And now, yeah, we will skip this relation to the complex. Yeah, I'm already a little bit behind my schedule. So I would like to discuss a nice relation of this conjecture to one of the conjectures I discussed in the beginning, one which resulted from the Calabi conjecture. So probably the most interesting unsolved problem related to this Calabi conjecture is when you take this C to be the set of all the balanced metric. And the balanced metric is just the one for which small omega to the power n-1 is declosed. So for this problem, we don't even have any equation which we need to solve in order to solve the conjecture. That's why the problem is actually very interesting. But nevertheless, even this special instantation of the problem is not solved. So suppose that you have a balanced manifold. So this is complex and this is the balanced metric. Suppose, moreover, that the canonical bundle of M is trivial. Can you find a balanced metric with Ricci tensor with respect to one of the connections being 0? And it turns out that if you can solve the quaternionic Monge-Ampère equation, or equivalently the conjecture posed by Alesker and Verbitsky, then you can answer a variant of that. So you don't have to assume even that your manifold admits some balanced metric, but instead of that, it has to admit HKT metric. Also, the I-complex structure actually has to be in the twist or sphere of some hypercomplex structure, which is also not a trivial requirement. But provided you have this, then if you are able to manage, if you are able to solve the quaternionic Monge-Ampère equation when you have the right-hand side being the holomorphic trivialization of the canonical bundle, then this metric which you will find will not only be HKT, it will actually be balanced. So you will solve a particular case of that problem, which may be the case that it's not solvable in general. So you'll obtain a nice class of examples when the problem is solvable, but provided you can solve the problem of Alesker and Verbitsky. Okay, so now to this quaternionic Monge-Ampère equation. So the problem is solved in certain cases. So firstly, it was solved in 2013 under quite heavy assumptions. So the assumptions were that you assume essentially that your manifold is a torus, and moreover, the hypercomplex structure which is endowed with satisfies this condition, which I told you usually hypercomplex structure does not satisfy, so that locally it looks like HN. So this is very heavy assumption. Another class of cases which is solved is when you assume some invariance either on a hypercomplex structure or on a metric, because then you can actually reduce this PDE to some other PDE, quasi-linear or maybe non-linear, but not that hardly unlinear as the quaternionic equation. And then you can solve it by some method known for easier equations. But without these either heavy assumptions on the hypercomplex structure or this invariance, nothing was known. And then in 2021, we had this paper with Dinev, when we managed to solve the problem without any assumption on the flatness of the hypercomplex structure. But we needed still pretty severe restriction. So the original metric, which in the conjecture of Alesker and Verbitsky is HKT metric, has to be hyperkala actually. So it cannot have torsion or stronger differentiability has to be assumed or on the original metric. And this for now stays to be the most general case under which the conjecture is solved. So the original conjecture is not solved as for today. Though in the meantime, there were some tries, but they didn't work out. So let me speak maybe a little bit about the technicalities if I still have time.
5 minutes.
5 minutes, okay. So yes, Professor Kozi already told you. When you have a elliptic PDE, let's say of the second order, but it's not important, on a manifold, usually, well, there are a couple of approaches, but still the most popular one is you use continuity method. So you somehow, so this is your PDE. Now its strategy is perturb F, let's say by parameter T. So consider F of T, family of functions. And set this family in such a way that, let's say, the ending point is the F for which you try to solve, and the beginning F is F for which you can trivially say that the PDE has a solution. Okay. So, for example, in here, a very wise choice is to start with F, which is actually constantly 0, right? Because then here you have 1. So we have omega to the power n on the right-hand side, and I can, from the spot, give you an explicit formula for the solution. Phi is just 0, right? This is very wise, but now you are forced to show that you can actually travel along the path. So you have to show that the set of times for which you can solve is open and closed, because then it will be the whole interval, right? Openness usually for those kind of equations is simple. It's simpler. It depends on some openness of the image of certain differential operator or inverse theorems in certain Banach spaces. So this is not trivial. This is not trivial, but not hard. the core of all the problems are a priori estimates because they are needed for the closeness. So you need to know that you have the bound on the solution on phi, which is dependent only on the norm of the right-hand side, so of the f, because it will be controlled along the perturbation path, and possibly on some fixed quantities like the curvature of the hypercomplex structure or the curvature of the initial metric, because they are not changing along the continuity path. And a general elliptic machinery tells you that actually all you need to establish are the estimates up for the derivatives up to the second order. Then the general elliptic machinery will tell you that you have the estimates for all the orders. Okay, so C0, C1, and C2 estimates are crucial, the only one which are needed. So for the for the C0 estimate, they were obtained in the increasing generality. So the first ones to obtain the C0 estimate under the assumption that the original metric is HKT, so precisely as in the conjecture, are Alesker and Shelukin, and they obtained the estimate in 2015. Then in 2019, I obtained this simpler proof. So I had the same assumption as Alesker and Shelukin, but my proof was reasonably easier. And if you go into details, actually, it also depended only on some LP norm of the right-hand side, while in their case, it depended on the SUP norm of the right-hand side. But for the continuity method, it's not crucial, so it's a very mild improvement. But then in 2022, I managed to prove actually that the C0 estimate holds regardless of the initial metric being HKT, and moreover, this estimate belongs only on LQ norm of the right-hand side for any Q bigger than 2, and moreover, this is a sharp result in certain sense. So this is an analog of a very famous result of Professor Kołodziej for the complex Monge-Ampère equation. For the complex Monge-Ampère equation, you obtain a C0 estimate, which depends on LP norm for any P bigger than 1, and this is again a sharp estimate. So regarding C0 estimate, everything is known. 1 down to more, so C1 and C2 estimate, and those are hard. So in this paper with Sławek Dinew from 2021, we managed to prove the gradient estimate, so the first order estimate, which depends only on the C0 estimate, and this one is already known, so we have really a gradient estimate. And also the estimate for the Laplacian, which is enough to have actually the full C2 estimate. But in both those estimates, we actually use the fact that the initial metric is hyperkähler and not hyperkähler with torsion. And this seems to be unremovable for now. And because of that, we are able to solve the original conjecture of Alesker and Verbitsky. So as I written in here, it says that with the beginning metric being hyperkähler, but actually if you go through our method, it works even if the original metric is not hyperkähler. We only have to have the guarantee that there exists some hyperkähler metric compatible with the hypercomplex structure, because then we can use it in our analysis. Okay, and since I'm a little over time, so I will skip the last slide. Thanks.
Thank you. So, are there any questions? If not, let's sum the paper again.
Thanks.